Hey, so we spent a week looking at main sequence stars, and we can apply really fun and exciting thinking and observation to learn a lot about them. That's 90% of the stars. We want to know about the others, and one of the things that main sequence stars taught us is that they're not eternal. They burn out, so if we see any, they must be forming. If we can ask what happened, where they came from, how it is that they form, and what happens when they are no longer able to be main sequence stars. What happens to a star when it's done? That'll be the topic of this week, stellar evolution. The challenge that faces us when trying to understand stellar evolution is that stars evolve, but very slowly. The time scale for the sun's evolution is tens of billions of years. We do not get to watch a star evolve. We get a snapshot of the universe as it is now, and so we will need, again, to apply both painstaking observation and modeling and understanding of the science to piece together a picture of how stars evolve. I spoke about sort of population studies as the realm of sociologists, I think, last week. Probably better analogy is the one I quoted on the title slide due to the famous British astronomer Sir William Herschel, who likened an astronomer to someone wandering through a beautiful garden and trying to understand by looking at the plants how it is that they develop and evolve and develop and grow. And you can relate, if you wish, the fully grown redwood to a sapling, even though no living biologist has seen a redwood sapling grow into a 4,000-year-old mature tree. We know enough about the way plants work to relate the two. And we have to learn enough about the way stars work to make the same observations about stars. One of the laboratories that we have to do this is star clusters. Clusters, remember, are formed when a cloud starts collapsing. That means all of the stars in a cluster are formed at the same time. Comparing the snapshot that different clusters give us at different times since they were created allows us to compare what the status is of different stars, all the different stars in a cluster, when they are the same age, and this gives us different snapshots of the population, and this will be an important tool in understanding what we know about stellar evolution. So the plan for the week is start by talking about how stars form. We'll talk about the pre-main sequence aspect of stellar evolution. We'll skip over the rather boring, sedate main sequence and talk about all the exciting things that happen after the main sequence. We'll mention giants and supergiants and dwarves and remnants and all kinds of exciting explosions. And in the process, we will have filled out the HR diagram, explained all of the things that are not main sequence stars that we have found, and pieced them together in an interesting pattern. We will discover many new phenomena and some new physics that will be required to understand them. More this week than in any previous week, we will be addressing questions to which the answer is not known, not just to me, but to mankind. And so there will be a lot of, well, some people think this and some people think that. I think that's very exciting. We will be acquiring more steps on our construction of the cosmic distance ladder, ways to measure larger and larger distances, to add more and more of the universe to our 3D picture of things to which we can determine the distance. We will not be discussing this week despite the fact that clusters play an important role in what we talk about, the dynamics of the formation of clusters, the molecular clouds they come from, and the dynamics of how clusters evolve are going to be relegated to our study of galaxies, since those are structures above stars. We will relegate them to galactic studies. Although some of the aspects of the physics we study will require relativistic physics, and we will skip that because relativity will be the topic for next week, and I hope you enjoy this one.